I'm going to go ahead and draw us an RC circuit here with a switch and a resistor and a capacitor. Okay. Alright, so what do we got here? The EMF is 12 volts. The resistance is 0.24 ohms. We don't know what the capacitor is, but we do know that it's initially uncharged. And then we're told at t equals 0.55 seconds, the voltage drop across the resistor is 3.5 volts. Well, if that's 3.5 and this is 12, I know that the voltage drop across the resistor plus the voltage drop across the capacitor has to equal the EMF, right? That's the loop rule. So that means the voltage drop across the capacitor at that time is 8.5 volts, which is what part A is asking for. Okay. Now for part B, that's a little bit more involved. Got to find the capacitance. I guess, there's a lot of ways to approach this. I guess I'll start with the voltage drop across the resistor. Or, well, no, I'll go ahead and do the capacitor, right? The voltage drop across the capacitor, that's Q over C. Now Q is C times the EMF times 1 minus e to the minus t over tau over C. So the C's cancel out, and I'm left with 8.5 is equal to 12 times 1 minus e to the minus t over RC. Right, because 8.5 is the voltage drop across the capacitor, and 12 is the EMF. Okay, so that goes to 0.7083 is 1 minus e to the minus t over RC. And then that works, if I subtract 1 from both sides and flip the signs, I get 0.2917 is e to the minus t over RC. And then I take the natural log of both sides. The natural log of 0.2917 is just brings that exponent down. And so I'm left with minus 1.23 is equal to minus the time, which, remember, the time is 0.55 seconds. And we divide by the resistance, 0.24 times the capacitance. So if I solve for the capacitance, I make both sides positive, and I solve for the capacitance, I get that it's equal to 0.55 divided by 0.24 times 1.23, which is 1.86 farads. Now that's a pretty big capacitance, but if you consider the resistance is 0.24, then if I figure out the time constant here, RC, 0.24 times 1.86, well, that's about half a second, right? It's about 0.4 seconds or so. And you notice that at t equals 0.55 seconds, the voltage drop across the resistor is about 1/3 of its maximum value. So the current has already dropped to 1/3. I guess I should go ahead and calculate this. 0.24 times 1.86, 0.4464. So that means that this time is pretty close to tau. So that capacitance is reasonable, right? We expect to have a pretty big capacitance for such a big time constant. Alright, anyway, part C. When 3 time constants have elapsed, what will be the voltage drop across the resistor? Well, our formula for the voltage drop across the resistor is that it's equal to the current times the resistance. And that's just, the current is I max times e to the minus t over RC multiplied by R. But I max is the EMF divided by the resistance. We're taking this whole thing and multiplying by R, so the R's cancel out. So I'm left with the EMF times e to the minus t over RC. Now, after 3 time constants have passed, That means that T is 3 tau. And so this is just 12 times e to the minus 3, which is 0.60 volts. That's it.